Alright, welcome everyone. In this video we're going to talk about centroids of lines and areas. I actually just recorded this video and the audio did not take, so this is my second go around. If this one doesn't work, well, I might just give up. Technology is not always my friend. Let's start by defining what you mean by a centroid. It's a common phrase, you may be familiar with it. What we mean by centroid is the center of gravity for an object with uniform density. Now the key to this is that it is a uniform density. Because it's uniform density, then what I can say is that it will be based on the geometry of the shape. I suppose you could say those are like assumptions that we're using here, is that the has to be uniform. And you can imagine, right? So if I had some object and it was heavily weighted at a different density on one side than the other, then that would massively affect where the centroid is. But if it's all uniform, then I know it's right about in the center of the shape. So that's kind of what it is. If I had to draw some kind of example, we'll take some random shape and put it on some kind of x and y axis. Let's say this is my x and this is my y, and I'm going to guess the centroid's like maybe here. And then we are going to label, or we're going to define, as the distance up from the x-axis as y bar, and the distance over from the y-axis as x bar. And this is if it's like a 2D area shape. There is a potential to do the same thing with some kind of line. What it looks like, crazy looking line. And where my axis is, let's say it's here, there's my y, and let's say we'll have x right here, and we'll have a centroid. Now the centroid clearly would not be on the line. It doesn't have to be on the shape in general. Maybe it's like, where would it be? Maybe here. But we get the same thing with our x bar and our y bar, and we'll generally call this C for centroid for either case, right? So either areas or lines, that's what we're going to be talking about today. Now if I want to define the centroid of that shape in general, what I could do is I could actually imagine that the whole thing's like a square or rectangle, and if we did it, actually square's more based on the definition. If we did it like that, then I know that it's right in the center of that square. Of course, that isn't exactly accurate. So as an alternative, what I could do is make it into like 4 different, squares or rectangles. Each one would have its own centroid, and then I would take the average of those 4 squares. And of course, it'd be more accurate if I broke it up into as many squares as I could. And you've probably seen this before in calculus, where you can take smaller and smaller shapes, approach a limit, and define what it would be. So this would be the definition of our centroid. It would be, centroid is going to be the integral of x dA. So our x distance over is a function of the area divided by the total area, and our y bar would be equal to the integral of y dA over the total area. Now we aren't actually going to do integration today. We are going to do integration in the second part of this video. So if you want to see the integration piece, jump to the next video. For the line, our x bar, same idea, except we have dl over the total length of the line, and our y bar would be the integral of the y centroid for each line segment times the length of the segment, are divided by the total length of the segment. So those are the equations that in general we'll be using over these next 2 videos, or to find centroids. Like I said, today we're not doing integration because we already know the centroid of many shapes, right? I mean, we all know the centroid of a square. Say it's a 2 by 2 square. We know it's right in the center, 1 over and 1 up, right? So I have a table of, and you can find these tables in almost any textbook that has statics, any statics textbook, or any place that you can talk about centroids, I suppose, of these common shapes. The rectangle one's probably the most poorly drawn. The easy way to remember what the centroid of a triangle is it's always 1/3 of the way of the distance away from the longer side. So in this case, what it is this height up here is like h over 3, 1/3 of the way, or 2/3 away from the other side, right? I think they would have been better off drawing something like this, and then have the centroid, and it would be 1/3 of the way over this way, 1/3 of the way up. It's always 1/3 of the way away from that stronger side. And you can see quarter circles, semicircles, spandrels, all sorts of good stuff. We also have lines down here. If you had a quarter circle arc, semicircular arc, you can just look up what these X bar and Y bars are. So instead of just looking it up, of course, we have to do something with it. So the other topic that we are actually focusing on today is when we add up our shapes, or if I can break a shape into many known shapes. What does that mean? Heck, I can't even understand myself today. So we're going to call this composite plates and wires. And the idea is that if I have some shape that maybe it's looks a little something like this here, so kind of, let's say it goes over here, and then it goes up over here, and then it goes down over here. Might have some shape like this, and I want to find the centroid of it. Of course, this isn't going to be in the table, but I can break it into multiple shapes that are in the table. So I could break it into two different triangles and a rectangle. And I know that the centroid of the triangles are 1/3 of the way over from each side. I know the centroid of the rectangle is right in the center, right? And we could call this shape A1, A2, and A3, and this would be like C1, C2, C3. If I did that, it's basically just a weighted proportion. So my X bar will be equal to the sum of my X bar times the area of that little piece, right? Divided by the sum of all of the areas combined. And same thing with the Y bar, sum of my Y bar area over the sum of all my areas. So for instance, for shape 1, you know, I have this little X bar, so I have this little distance over here, that's my X bar 1, and then I have the times area 1, and I'd have plus X, no, I didn't plan on doing this, X bar 2 plus A2 plus X bar 3 times A3, and then the whole thing is divided by A1 plus A2 plus A3. So anyways, let's look at an actual example so we can get an idea how this works. Let's say this is the general shape that we're looking at, and we want to of course find this centroid. So the first step is to say, well, what kind of shapes can I break it into? And what I see is if I were to draw a line straight over, I'd have a rectangle and I'd have two triangles. So we can talk about this. I'm going to call this rectangle shape 1, the upper triangle shape 2, the lower triangle shape 3. And I'm going to create a little table to help keep it all straight. So I'm going to have like the area of each shape, and give myself plenty of room. I also want to find the X bar for each shape, the Y bar for each shape. Then I'm going to multiply my X bar times my area and my Y bar times my area. So once all said and done, what I'm going to do is I'm going to add up the total. So looking at area, shape 1 and finding the area, it's just a rectangle. If I add up 54 and 172, I end up with 126. So 126 times this 70 or times 54 is equal to 6804. So that's the area of the rectangle. The area, well, let's just do the whole rectangle and then I'll do the other one. So for the X bar for this rectangle, we'll have to say where is it, and I know it's halfway over, right? So it's like right there. I'll have to say, well, I can't put it as being 63, right? I know 126 over 2 is 63, but that's not relative to this Y. Remember, it would be this little distance right there. So that little distance there would be my 63, but I have to subtract out that 54, which gives me 9. So my X bar, I have 9. Y bar is a little easier because it's from the x-axis. I have 27. Multiply those through, I get 61,236 and 183,708. Shape 2 is a triangle. The area of a triangle is 1/2 the base times the height. So I have 1/2 times 126 times the height of 30, and that gives me something like 1890. Now for my X bar, this is where I said it's, you know, it would be located right about there, which is 2/3. It's 1/3 away from the longer side, so it'd be 2/3 away from the other side. Oh, I didn't even do it the right way. 2/3 from this side, right? So if I'm 2/3 of that, you know, I don't know. I didn't do this math ahead of time. I just have the answers written down, but I have 2/3 of 126. What's that give me? Something like 84 And then I need to take out that 54, and I end up with 30. So that's where that X bar comes from. Y bar, now I have to add in this little 54 before I go 1/3 of the way up. So 1/3 of 30 is 10, and then I have this other 54. So my Y bar would be 64. Multiply that through, I get 56,700 and 120,960. For shape 3, once again a triangle, so 1/2, 72 times 48 is my area, gives me 1728. For my X bar, I'm just 1/3 of that 72. Oh, sorry, I'm 2/3 of that 72, which is 48. And my Y bar, now you do have to be careful with this because Y bar is going to be in the negative direction, so I want to keep that sign in there. So I'm going to have negative 16, or 1/3 of 48 is 16, but I need that negative in there. Multiply that through and end up with 82,944. And I'm going to keep that sign in here, negative 27,648 for the Y bar area for that last triangle. Doing my summation, I end up with 10,422 for the total area of all 3 shapes. I have 200,880 for the sum of my X bar areas and 277,020 for the sum of my Y bar areas. So the last step, plugging it into this equation that we just did for our composite sections, what I have is this for the X bar, 200,880 divided by the total area of 10,422 gives me a value of like 19.27 millimeters. And same idea for the Y bar, 277,020 divided by 10,422. My computer sounds like it's about to take off with this fan going. I don't know what's going on. 26.6 millimeters. I tell you, first I have issues with the microphone. Now this fan, I don't know. The Surface Pro, you're not doing me right. So the last step would probably be to say, does that kind of make sense? And you go in and say, well, let's see, 19 over, and you know, what do I have, 26 up? So yeah, that seems pretty good. So that's what we're doing, and hopefully that was helpful, and thanks for watching.